So we'll look at a few more with partial fraction decompositions to find inverse Laplace transforms. So this one you might say, well, we did this with completing the square earlier. And you can do that. If you did that, you're going to encounter hyperbolic trig functions. So I would suggest when you look at a problem like that, if you can factor the denominator, do that as opposed to just taking off and completing the square. So if we look at this one, notice you can factor that denominator as s minus 4 times s plus 1, because minus 4s plus s gives you minus 3s. Negative 4 times 1 gives you negative 4. So here again we have two linear factors. So we can write it as a constant over the first linear factor plus a constant over the second linear factor. Do the same thing we've been doing, multiplying both sides of the equation by this denominator. That's all we're doing here. Here the whole denominator cancels, you're left with 10. Here the s minus 4's cancel, so a gets multiplied by s plus 1. Here the s plus 1's cancel, so b gets multiplied by s minus 4. So again, when you have the linear factors, you can just substitute in the numbers that make each factor 0. So if I put negative 1 in here, that term goes to 0. Here we have minus 1 minus 4, which is minus 5b. We still have 10 on the left, so b is negative 2. If we put 4 in here, this term's going to go to 0. So I'd have 10 equals a times 4 plus 1 plus b times 0. This gives us 5a, so a is 2. So we know our a and b for our partial fraction decomposition. So a is 2 and b is negative 2. So that's all we've done here. We're just taking the inverse Laplace transform of 2 over s minus 4 minus the inverse Laplace transform of 2 over s plus 1. So this is like the formula a 1 over s minus a, where a is 4. This one is like 1 over s minus a, where our a would be negative 1. So this is just that 2 times e to the 4t, because a is 4. We have a minus 2, and times e to the at, where a is negative 1. So if you can factor that denominator, do that, and you'll have the two linear factors. Well, we haven't seen one like this. In this case, the denominator has a linear factor that's repeated. It's squared. So how do you handle that? If you remember that from calculus, you take a constant over the linear factor plus another constant over the linear factor squared. If that was to the third power, we'd have a plus c over s minus 1 cubed, and that pattern would just continue. All right, so we multiply both sides of the equation by the denominator here. So here the denominators cancel, so you're left with 2s. Here one of the s plus 1's cancels, so you get a times s minus 1. Then here the denominator cancels, so you just get plus b. Now if we expand, there's probably different ways you can do this, but if you expanded this and compared like terms, we get as minus a plus b. The constant term here is minus a plus b, and then we have an a times s. On the left-hand side, we have 2s, so that's the same as 2s plus 0. The constant term on the left is 0. So if you compare like terms, the coefficient of s on the left is 2, on the right it's a, so a is 2. The constant term on the right is minus a plus b. The constant on the left is 0, so minus a plus b is 0, which tells you the b is equal to a and a is 2. So both a and b are 2. So we go back to our expression here. A is 2 and b is 2. That's what we have here. So this one is just 2 times the inverse Laplace transform of 1 over s minus a, where a is 1. So that's just 2 times e to the t. For this one, compare that to 1 over s squared, where you're shifting by a equals 1. It's an s minus a there. So it would be the t right there. You have the 2t, and then you multiply by e to the t to shift it by that s minus 1. So here are just a few little review problems, thinking back at what we've been doing for the last few days. So if you, these just have different kind of formats. So here we have an s squared plus 2 in the denominator. That means k is square root of 2, but you have the k in the numerator too. So that's like k over s squared plus k squared. So that inverse is just the sine of the square root of 2. And I've written parentheses so everybody understands that the square root of 2 just gets multiplied by the t. If I have s over s squared plus pi squared, and I want that inverse Laplace transform, here k is pi. So when you have s over s squared plus k squared, that inverse Laplace transform is just the cosine of kt. Here our k is pi. Now this one, suppose I had an s over an s minus 1 squared plus 4. How do you handle that? Remember, we're shifting in this argument in the denominator. I need the argument shifted by the same amount in the numerator. So I need an s minus 1 in the numerator, so I can write it that way. But if I subtract 1, I have to add 1. So, but it's all over the same denominator. So here I have the s minus 1 over that denominator with the same shifted argument. And here I have the constant over an s minus 1 squared plus 4. Our k is 2 for both of these. This one goes with the sine. I need k over it. So our k is 2. I can put a 2 there and multiply by 1/2 in the front. And so the first one is like the cosine of kt formula, but I've shifted. I have an s minus a where a is 1. So I get the cosine of 2t and have to multiply by e to the t. Here, this is the sine of 2t times this 1/2 out in front, but I have to shift. I have the shifted argument, so I'll multiply by e to the t.